Welcome to our presentation for ELEC 291 Project 2. Our goal was to design a field tracking robot capable of autonomous navigation and complex manual override. While many teams rely on standard architectures, we pushed our system's complexity by implementing a dual processor ecosystem, an STM32L051 on the robot, and EMF8 on our custom remote. My name is Krish Vashist, and today I will detail how we overcame hardware failures, transitioned from failed PCBs to robust breadboard prototypes, and how we engineered this project from ground up. Our system is split into two distinct control hubs. The remote controller, powered by the EMF8 LB1, manages user input, haptic feedback via the coin vibration motors, a speaker for audible status alerts, and an LCD for an advanced user interface. On the other hand, the robot utilizes STM32L051. It handles high current demands of the L298 and dual H bridge, driving our DC motors, the link between custom IR transmission chain. We used IR LEDs on the transmitter and a receiver such as TSOP331 on the robot to translate high frequency bursts into actionable movement commands. Rather than using a standard NEC protocol, we designed a custom communication layer inspired by multiple pulse width modulation standards. We designated specific bursts of 38 kHz signals, for example, 16 cycles for header, 8 for logic 0, 32 for logic 1, all separated by a constant 500 microsecond space. On the robot side, we used a hardware timer to record ADC readings of this IR receiver output, translating these timings into 4-bit command structure. This allowed us to map specific nibbles such as 0010 for forward or 1101 for backwards, and dedicated codes for autonomous path selections like 0110 for path 1. The remote further enhances the user experience by using a coin-based haptic device. Depending on the path observed on the command set, the user receives physical feedback, such as the specific vibrations for path complete or obstacle proximity. This creates a closed-loop feel between the user and the machine. Here's our list of bonus features. Our first major bonus feature is the triple microphone array. Using 3 GY Max 4466 sensors, we implemented sound triangulation. The STM32 processes the time of arrival across 3 ADC channels, allowing the robot to autonomously turn and face a sound source in our follow to noise mode, or react to clap to start commands. For example, a clap of 4 times made the robot move forward by certain steps. Our second biggest bonus feature was implementing a new mode called the learning mode. In this mode, we used a PMW3901 optical flow sensor, which allowed us to map the surface and allowed the robot to follow a path that was preset by the user. Central to our user experience is a custom-designed smartphone app connected via the HC06 Bluetooth module. This app provides 4 distinct operational modes. Manual mode, which involves precision joystick control. Guide wire mode for the automated tracking. Learning mode for autonomous retracing of a previously navigated path. And finally, the noise mode, which is for sound navigation. Here's our demo. Engineering, as we all know, is rarely a linear process. We faced many major setbacks. One of them was when our custom PCB failed to operate due to recurring reset issues with the LCD interface. Rather than stalling, we pivoted back to the breadboard design. We learned an early lesson that our initial H-bridge iterations were not as clean as required. This was leading to many hours of debugging. By rebuilding the circuit with a focus on clean building, we then saved dozens of more hours which may have been required for later debugging phases. The biggest setback of all was our guide wire tracking. We spent countless hours debugging the issues and unfortunately couldn't demo our project in our allotted Wednesday section. We later realized that the speed of the robot was the major reason why it kept failing to follow the magnetic wire and do successful intersections. We then implemented a PWM to slow down the robot by 50%. This came out to be a success, and our team was able to demo the following Thursday. Through these iterations, we moved from simple LED blinking to a multi-processor, multi-protocol robotic system. We successfully implemented a custom communication stack, a haptic user interface, and precise optical flow navigation. This project proved to have many major setbacks, but we believe that these are mere opportunities to refine our hardware robustness and learn from our mistakes. Thank you so much for watching our presentation. This is it for ELEC 291. Stay tuned for 391 projects. Goodbye.
Sitting here where the sun sets low, golden rays painting skies of